Swayam Prabha. Digital India. Educated India.
So today we will learn the Gram-Schmidt process. The Gram-Schmidt process produces an orthogonal basis of a inner product space. Okay. I have a vector space, then it has many kinds of bases. Okay. We would like to have a basis of this inner product space. This is an inner product space, and suppose the dimension of V is equal to n. We fix a basis of this inner product space, and we want to apply this process called Gram-Schmidt process, and it will result in a new basis. Okay, it will result in a new basis so that the elements in this basis, the vectors in this basis, they are mutually perpendicular. Okay, and if we desire them to be unit vectors, we can always divide by their length and get a new basis. So whenever this condition is satisfied, that is the vectors in this basis are mutually perpendicular, then this is called an orthogonal basis. Orthogonal basis, okay, of V. And if in addition the vectors have unit length for each I, then this vector is called, or this basis is called orthonormal basis. Okay, we are used to orthonormal basis. In R3 we work with IJK. Okay, IJK, the standard basis, and they are mutually perpendicular, they have unit length. So when we have an inner product space, the best basis to work with is an orthonormal basis. But a vector space comes with some basis constructed by some process. We can apply this Gram-Schmidt process to convert a given basis into an orthogonal basis or orthonormal basis. Yeah. So let us look at the formal statement of this. Okay. So suppose I have a subspace. I have subspace of this vector space. Okay, and I have a basis. I have a basis of this vector space also. By some method, I have access to a basis of this subspace. Okay, and suppose this is an orthogonal basis. Okay, W is a subspace. Its dimension could be 1 or 2 or whatever, but we have constructed a orthonormal basis of this subspace. Yeah, then there exist additional elements Wm plus 1, Wn of the whole space, so that W1 up to Wn is a orthogonal basis of V. So in other words, if I am given mutually perpendicular vectors, a finite set of mutually perpendicular vectors, then we can enlarge this set to a larger set which consists of n mutually perpendicular vectors. Okay, n is the dimension. Yeah. So we proved earlier that mutually perpendicular vectors are linearly independent. So if the vector space has dimension n and I have n mutually perpendicular vectors, they are going to be linearly independent, and therefore they will form a basis. So Gram-Schmidt process starts with one set of mutually perpendicular vectors, and then it can enlarge it to a basis of the whole space, so that vectors in this basis are mutually perpendicular. Okay. The proof will be an algorithm. We will produce an algorithm to construct such a basis. Okay. And by taking, say, one single vector, if you take one single vector which is non-zero, then it is automatically orthogonal. Okay, there is no other vectors to compare with, and it says, the Gram-Schmidt process says that I can enlarge this singleton vector to a basis of the whole space so that it is an orthogonal basis. So starting with any vector, we can construct other vectors which are mutually perpendicular, and they are all perpendicular to this single vector. So say in three-dimensional space, what does it say in three-dimensional space? Okay, in three-dimensional space, it says that I can start with any vector. Yeah, I can start with any vector. Okay, and then I can enlarge this vector to a set of three vectors so that they are mutually perpendicular. Geometrically, what are we going to do? Yeah, I will take a plane which is perpendicular to this vector. Yeah, a plane which is perpendicular to this vector. Inside this plane, I will need two vectors which are perpendicular. So I will have three vectors which are perpendicular to each other, and in our three vectors which are mutually perpendicular are going to give me a basis. Okay, so this is Gram-Schmidt process is a generalization of that I can start with any set of mutually perpendicular vectors, then it can be enlarged to a set of mutually perpendicular vectors which will constitute a basis of the ambient space V. So let us see what the algorithm is. So this algorithm is called Gram-Schmidt orthogonalization process. So the input is a basis, yeah. Output is a basis again of the same vector space, okay, and it will be a set of mutually perpendicular vectors which will form a basis. Okay, so let us begin. So I am given a set of mutually perpendicular vectors which are forming a basis of W, and if W is not equal to V, then I want to enlarge this mutually perpendicular vectors inside W to a basis of V. So suppose W is not equal to V. Yeah, then there is a vector in V which is outside W. And we have seen that if I take a vector which is outside the linear span of given set of vectors, then this new set of vectors is going to be linearly independent. Yeah, this set is a linearly independent set of vectors. So it will form a vector space of dimension m plus 1. Yeah, it will form a subspace of dimension m plus 1, but this may not be orthogonal. Right? Vm plus 1 may not be perpendicular to these wi's. Wi's themselves are perpendicular to each other, but Vm plus 1 is may not be perpendicular to W1 up to Wm, and so we would like to modify Vm plus 1 to get a set of mutually perpendicular m plus 1 vectors. So here we use this idea of projection. Last time I explained the idea of projection. So idea of projection was that I have a direction W and I have a vector V. Okay, then I can decompose this vector V into two components. One will be in the direction of W, which is called the projection of V in the direction of W. And if I subtract from V this projection in the direction of W, then I get a vector which is V minus the projection of V in the direction of W, and we showed that this is perpendicular to the projection vector. Yeah, and the formula for the projection it is derived by using dot product. Okay, here we are working in inner product space, and this is equal to inner product of W with V over square of length of V times W. So it is a scalar multiple of W. Projection of V in the direction of W is a scalar multiple of W, but that scalar is the inner product of W with V divided by norm of W square. Yeah. So if norm of W is 1, if it's a unit vector, then this is equal to inner product of W with V, yeah, times W. So PWV equal to this. Okay. So PW, the projection map is taking vectors and producing vectors which are in the linear span of W. This is a one-dimensional subspace. It is consisting of all scalar multiples of W, and input is a vector, output is a projection of that same vector in the direction of W, and this formula says that PW is a linear transformation. Yeah, this map which is projecting vectors onto this line passing through W is a linear transformation. Yeah, PW, the projection map from V to this subspace which is spanned by single vector W. This is a linear transformation. Yeah. So from the product properties of inner product is linear in the second coordinate. Yeah, it is a linear transformation, and of course, what happens to W? Where is W mapping to? W is equal to inner product of W with W times W, and that is equal to W. So all vectors in the direction of W, they are fixed by the projection. Okay, geometrically this is clear. When I take a vector in the direction of W and project it in the direction of W, I get the same vector. Yeah. So this PW is onto, yeah, W is mapped to W. So any scalar multiple of W under this projection map is also mapped to the same scalar multiple. So therefore the image of the projection operator is this one-dimensional space. Okay, image of the projection vector is this one-dimensional space, and we know how do we define rank of a linear transformation. Rank of a linear transformation is the dimension of the image, and in this case dimension of the image is 1, because the image is one-dimensional subspace which is a linear span of a single vector. So rank of projection operator is 1, and what is the null space? Null space of the projection operator, it is set of all V, so that the projection along the direction of W is 0. Okay, and this is the set of all vectors in the whole space which are perpendicular to W. Yeah, they are perpendicular to W. So if say let us say V1 in three-dimensional space, and my W is in the direction of x-axis. Okay, take a vector in the direction of x-axis. Okay, if my W is equal to just the unit vector I, then the null space of the projection operator with respect to this unit vector I is all vectors which are perpendicular to the x-axis, and that is the YZ plane. Okay, yeah. So therefore the null space is all vectors which are perpendicular to W. Right, but we know the rank nullity theorem. What is the rank nullity theorem? The projection operator from V to W, it says that the rank of the linear transformation plus the nullity of the linear transformation is equal to dimension of V, and therefore the nullity of PW is simply dimension of V minus rank of PW. Rank of PW is 1. Okay, so the nullity of the projection operator is 1 less than the dimension of V. Okay, so if V was R3, then the nullity is 2, and so the null space is a two-dimensional subspace, and you know that two-dimensional subspace is a plane passing through origin, and that plane in this case is exactly the vectors which are perpendicular to the given vector W. Okay, that is how projection operator is working, and we want to now exploit this property of projection operator, that if I subtract from V the projection in the direction of W, I get a vector which is perpendicular to W. So V minus the projection of V in the direction of W, this is perpendicular to W, and therefore this is always in the null space. This is always the null space of the projection operator. Okay. So we will exploit these things to construct a basis, orthogonal basis. So what do we do? This is the first step of the Gram-Schmidt orthonormalization process. Yeah. So we were given a set of vectors, and I have a vector which is outside this. Okay, outside this Vm plus 1. Okay. Now our subspace W is already provided with the orthogonal basis W1 up to Wm, and Vm plus 1 may not be perpendicular to these Wi's. What I can do? I can project Vm plus 1 in the each of these directions. Okay, and add them. So take the projection of Vm plus 1 in the direction of W1, projection of Vm plus 1 in the direction of W2, and projection of Vm plus 1 in the direction of Wm plus 1. Okay, yeah. So V is the big space and W is the smaller space. Okay, and I take a vector and look at its projection in the direction of W1, look at the projection in the direction of W2, etc. The projection of V in the direction of W1 is a scalar multiple of W1. Projection of V in the direction of W2 is a scalar multiple of W2, etc. So when I add these vectors, of course, it's a linear combination of W1, W2, Wm, and therefore this is a vector inside W. Okay. So given a big vector space, I have a vector in that big vector space. I have a smaller subspace. So I always think of plane passing through origin, and I have arbitrary vector in R3. I want to project that vector inside this subspace. So this is the natural way to do that. Take the projection of V in each of the direction of the orthogonal basis W1, W2, Wm. Okay, and then take their sum, and that's a vector inside W, and this is called the projection of V inside W. Yeah. So this is what we are doing, and we take the projection of Vm plus 1 in each of these directions of the orthogonal basis of W, and subtract this from Vm plus 1. Okay, subtract from Vm plus 1. Yeah. Now this vector, let us see. If suppose this Wm plus 1, after I subtract the projections in each of the directions, suppose this Wm plus 1 is 0. That means Vm plus 1 is a linear combination of W1, W2, Wm, but that will say that Vm plus 1 is in the subspace W, but this is not correct. Yeah. So when I subtract the projections in the directions of Wi's from Vm plus 1, and Vm plus 1 was outside the subspace, I get a non-zero vector. This vector Wm plus 1 is a non-zero vector. Okay. Yeah. So there is this projection inside W, and I have subtracted that vector, and this vector is what we want to prove, that it is perpendicular to each of the Wi's. Okay. We will check that this is an orthogonal set of vectors. We wanted to enlarge a given set of vectors into a orthogonal set of vectors, and this is what we did. We constructed this Wm plus 1 from Vm plus 1. Okay. So let us show that this is orthogonal. Now W1 up to Wm, they are mutually perpendicular, nothing to check. We have to only show that Wm plus 1 is perpendicular to every Wi. Okay. Wm plus 1 is perpendicular to Wi for every I. So you take the inner product of Wi with Wm plus 1. We want to show it is equal to 0. Yeah. The definition of Wm plus 1 is, it is Vm plus 1 minus the sum of the projections of Vm plus 1 in each of the directions W1, W2, Wm. So Wi inner product with this vector, but inner product is linear in the second coordinate. Yeah. So this is equal to, I can split this as Wi Vm plus 1 and Wi inner product with these vectors. Okay. But this is a sum, this is a linear combination of W1, W2, Wm. This vector is some alpha 1 W1 plus alpha m Wn. Okay, so therefore I can again apply multilinear property of the inner product and get that this is equal to Wi. As this sum can be taken out, but I know that Wi with Wj inner product, that is 0 when I is not equal to j. So only one term will survive here, and that is the scalar multiple of Wi. Others are scalar multiple of Wj, they are perpendicular to Wi when I is not equal to j. So I am left with this, okay. But Wi inner product with Pwi Vm plus 1. Yeah, what is that? They write the projection formula. Projection of Vm plus 1 in the direction of Wi is this vector. Take the inner product of Wi with Vm plus 1, divide by the square of length of Wi times Wi. Okay, this is a this number comes out of the inner product because it is in the second coordinate. Inner product is it is linear in the second coordinate, so this number comes out, and I'm left with Wi inner product with Wi, and that is equal to this is equal to square of the length of Wi, and I'm left with Wi time inner product with Vm plus 1, and therefore it is equal to 0. Yeah. Okay. So I just substituted the formula for projection of a vector in the direction of Wi, and that led to the proof that this new vector Wm plus 1, which I constructed, okay, by subtracting projection of Vm plus 1 in each of the previous orthogonal directions from Vm plus 1, then this says that this new vector is perpendicular to the old vectors. And so now I have a bigger set of vectors which are mutually perpendicular. Yeah. Now you can repeat this process. Suppose this m plus 1 vectors do not span the whole space. Then there is another vector which is outside this. Now repeat this process, and to enlarge this to a bigger orthogonal set of m plus 2 vectors. Now this process cannot continue forever, because V is n dimensional. As soon as you get n vectors which are perpendicular to each other, then I would have constructed n linearly independent vectors, and these n linearly independent vectors therefore will form a basis of W, and that is called the orthogonal basis. Yeah. Yeah. So this is the Gram-Schmidt process. Yeah. This is the Gram-Schmidt process. So let me illustrate this with the real vector space of polynomials. Yeah, polynomials of degree at most 3, and suppose they are defined on -1 to 1. Of course, polynomials are defined on a whole real line. But in order to make a inner product space out of polynomials, we have to think of them acting on a closed bounded set, because the inner product is defined through an integral. Yeah, inner product is defined through an integral. What is the inner product? Inner product of two functions which are continuous on this closed bounded interval -1 to 1. You just take the product of those two functions and integrate. Okay, this is a number. This is a number, and by properties of integral, you can check that this is a inner product. So we shall use this inner product for this inner product space of polynomials of degree at most 3. But polynomials of degree at most 3, one standard basis is 1x, x square, x cube. This is a basis of polynomials of degree 3, right? But you see, when I integrate, when I take the inner product of 1 and x square, it doesn't give me 1 and x, it gives me 0, but inner product of 1 and x square, inner product of 1 and x square, yeah, is this, which is equal to x cube over 3 -1 to 1, and that is 2 over 3. So it is not 0. So 1 and x are not, 1 and x square are not perpendicular. Yeah, 1 and x are perpendicular. Okay, 1 and x are perpendicular. So these four vectors, these four polynomials, they are not perpendicular to each other. Gram-Schmidt process will take this as the input of this inner product space of polynomials of degree at most 3 and produce a orthonormal basis. Yeah. So let us Let us recall this process. So we start with the basis of V, yeah, and we can start with any of these, but the simplest is 1. So take the constant polynomial 1, and this is my first vector W1. I want to now construct W2, which is perpendicular to W1, okay, which is perpendicular. So I bring in this x, okay, bring in this x. X is not in the linear span of 1. Yeah, x is not a scalar multiple of 1. So 1 and x are linearly independent. And so in order to get the second vector, which is perpendicular to W1, I will take projection of x in the direction of 1. Okay, take the projection of x in the direction of 1 and then subtract. Okay, this is the projection of x in the direction of the constant polynomial 1 by definition of projection, and subtract from x. And we know by general principle that this vector is going to be perpendicular to 1. Okay, so simply substitute the definition of inner product of x with 1. It is minus 1 to 1 times x times 1, which is becomes t, and this is equal to just x. Okay, so because we knew that 1 and x are linearly independent, they are mutually perpendicular. So second vector is automatically, it has come out as x itself. There's no change. Yeah, if you apply Gram-Schmidt process on vectors which are mutually perpendicular already, it doesn't lead to anything new. It will produce the same basis. You can check from the definition of Gram-Schmidt process that if you don't apply this on mutually perpendicular vectors, because the effect is the same, it will produce the same set of vectors. That's what happened here. 1 and x were mutually perpendicular, so the Gram-Schmidt process did not change these two vectors. Okay, now let us look at W3. Okay, 1 and x, they span a 2-dimensional space in this 4-dimensional space. Yeah, 1 and x form a 2-dimensional space, and outside this there are x square and x cube. Okay, so we now take x square, and I want to produce 3 mutually perpendicular polynomials. So what is the method? Take x square, take its projection along 1, take its projection along x, and add those projections. Then I will get a vector inside this 2-dimensional space, which is spanned by 1 and x, and from x square subtract this projection of x square in the subspace spanned by 1 and x. And so that is W3, x square. From x square subtract, this is the projection along 1 of x square, this is the projection of x square along x. Okay, and then substitute the formula for inner product in terms of integral, and you will get x square minus 1 over 3. Okay, so now I have 1 and x square minus 1 over 3. You can check that x square minus 1 over 3 is perpendicular to x. It is also perpendicular to 1. Okay, now I want to, because it's a 4-dimensional space, we have to construct one more vector W4, and you see 1 x and x square minus 1/3, it doesn't contain x cube. Yeah, no linear combination of 1 x and x square minus 1/3 can give you x cube. So x cube is outside the linear span of these 3 vectors, and therefore I can start with x cube and take the projection of x cube in the direction of 1, projection of x cube in the direction of x, and the projection of x cube in the direction of x square minus 1/3. So previously constructed vectors, I have to take previously constructed mutually perpendicular vectors, and I pull a new vector and take its projection along these 3 directions, add those, and then subtract from x cube. I will get a vector W4, which is perpendicular to W1, W2, W3. And so these, so I get this vector. Yeah, if I do this, and it turns out to be x cube minus 3x over 5. Okay, so these three polynomials, x cube minus 3x over 5, x square minus 1/3, x and 1. These 4 polynomials are going to be mutually perpendicular. Their length may not be 1, but I can divide by the length. To find length of a vector, I have to just take the inner product of vector with itself, and then take the square root, that is the length. So we can always, convert this 4 vectors which are mutually perpendicular into 4 vectors which are mutually perpendicular, and after divided by the length, they will be of unit length. Okay, and we can get orthonormal basis. we did this for polynomials of degree at most 3, but this process can be continued. You can take a vector space of polynomials of degree n defined on a closed bounded interval, yeah, then this forms inner product space, and out of this basis of n plus 1 polynomials 1 x, x square, xn, we can construct new set of polynomials which are mutually perpendicular. Okay, these polynomials that we get, they have definite formula. They are called Legendre polynomials. Yeah, where if I input is 1 x, x square, xn, and apply the Gram-Schmidt process, I will get polynomials of degree 0, 1, 2, n, and these are called Legendre polynomials. They have a formula. You can look at any textbook. You will see a formula, and these Legendre polynomials, you will meet them in a differential equation course, and they turn out to be solutions of some differential equation. Okay, so that's the Gram-Schmidt process to construct a orthogonal basis of a given vector space, starting from any set of mutually perpendicular vectors. Okay, now let us discuss the concept of orthogonal subspace. Okay, orthogonal subspace of a subspace. We have come across this already. Suppose I have a plane in 3-dimensional space. Orthogonal subspace of this plane will be all vectors which are perpendicular to this. So all vectors which are perpendicular to this will be along the line passing through origin, and take the vector, one vector which is perpendicular to this plane, and take all scalar multiples. So if W is this, then W perpendicular will be all vectors which are along this line passing through origin, and these are perpendicular to W. Okay, so these two subspaces, yeah, if you add them, you will get the whole space. Okay, so we want to now generalize this concept, and starting with any subspace of inner product space, finite dimensional inner product space, I want to pass to another subspace so that vectors in this subspace are perpendicular to all the vectors that you started with. Okay, we did this in Gram-Schmidt process. In Gram-Schmidt process, I had a mutually perpendicular set of vectors in a subspace, and then I constructed a vector Wm plus 1 which were perpendicular to every Wi which were previously constructed. Okay, so now we look at all vectors which are perpendicular to vectors in a given subspace. Okay, yeah. So let W be a subspace of V, and look at W perp, which is all vectors in V which are perpendicular to every vector in W. Okay, every vector in W, they are perpendicular. Okay, first of all, this is a subspace. W perp is a subspace. Yeah, W perp is a subspace of the same vector space. I start with W and look at W perp. Okay, this is again a subspace of V. What is W perp? W perp is all vectors so that they are perpendicular to every vector in W. Okay, so if I take two vectors which are perpendicular to every vector in W, then their linear combination will also be perpendicular, because linear combinations, the inner product is bilinear. Okay, so W perp is going to be a subspace, because if I add two vectors which are perpendicular to every vector in W, their sum is also perpendicular. Similarly, scalar multiple of a vector which is perpendicular to W will also be perpendicular to W. Yeah. What is interesting is that these two subspaces, they intersect only in zero vector. Yeah, they intersect only in zero vector, because suppose I have a vector which is non-zero, and it is in the intersection. Okay, then this W is in W, it is also in W perp, but W every vector in W perp is perpendicular to W. W is here, so it will say that inner product of W with W is 0. But this says by positive definite property of inner product, it says that W has to be 0. Okay, so W and W perp they intersect in 0. Only the 0 vector is perpendicular to is every vector. Vectors in W which are perpendicular to every vector in W are only the 0 vector. Okay, yeah. So this subspace W perp is called orthogonal complement. It is called orthogonal complement of W in V, and if I have W1 and W2 two subspaces, and then I define this new concept called direct sum of W with W1 and W2. Okay, so direct sum of W1 and W2 is the vector space which is linear span of W1 and W2. Yeah, it is the sum of these two vector spaces, and so that their intersection is the 0 vector. So whenever I have two subspaces, we intersect only in the 0 vector, and these two subspaces, the linear span of vectors in these two subspaces, the whole space, then we say that the whole space is the direct sum of W1 and W2. So for example, R3 is the direct sum of x-axis and the yz plane. Yeah, x-axis and the yz plane. YZ plane is 2-dimensional, x-axis is 1-dimensional, and every vector in R3 is a linear combination. It's a sum of one vector in the direction of x-axis and two vectors in the direction of y and z axis. So every vector in R3 can be written as a sum of two vectors, one in the x-axis direction, one in the yz plane, but the intersection of x-axis and yz plane is only the 0 vector. So we say R3 is direct sum of x-axis and the yz plane. This is now generalized to arbitrary subspaces. Whenever two subspaces are such that their intersection is 0 and the sum is the whole space, we say that V is the direct sum of W1 and W2. Yeah. Now let's show that whenever V is a direct sum of W and W, if I take W perp, W and W perp they intersect in 0 vector, but let us show that their sum is the whole space. Yeah, and every vector in V can be written as a sum of two vectors. One is in W, another is in W perp. This is just like here. Every vector in R3 is a sum of a vector along x-axis and a vector in the yz plane. Yeah. What is important is that these two components are uniquely determined. Yeah. One vector is coming from W, another vector is coming from W perp, and these vectors, if I can write any vector as a sum of these two vectors, one in W and another in W perp, these x and y are uniquely determined. Okay. Moreover, the dimension of V is the sum of the dimension of W and W perp. Okay. Let us see how to prove this. Yeah. So take a orthonormal basis of W. We can construct orthonormal basis of any subspace of an inner product space. So suppose I take a orthonormal basis V1 up to Vk of W. Okay, then I take the vector V. I take a vector V. I want to decompose the vector V as a sum of two vectors, one inside W and another in W perp. Okay, so what do? We take this vector V and take its projection in the direction of V1. Now this is the orthonormal basis. They are unit vectors which are perpendicular to each other. Okay, so I can take the projection of V in the direction of V1. This is the projection of V in the direction of V2, and this is the projection of V in the direction of Vk, and add them. This is a vector inside W. Yeah. So this vector V is arbitrary vector in the big space. I am taking its projection inside W. The projection of a vector inside W is simply the sum of the projections in mutually perpendicular directions. Yeah, these mutually perpendicular directions, I have now set them as a unit vectors, so that the formula becomes simple. We don't have to divide by length of VI's. Okay, so this is I am taking projection of V in the mutually perpendicular unit directions V1 up to Vk, and this is a vector in W. And now I will take y to be V minus x. Once I have determined x, then y is forced on us. Y is v minus x. Okay, so let us y is equal to v minus x. So x is constructed out of v and y is v minus x. Now what we have to prove that this is the desired decomposition. X is coming from w. I want to show that this y is coming from w perp. Okay, so that means we need to show that v minus x is perpendicular to every vector. Okay, it is perpendicular to every vector in V for all w in W. So let us do that y belongs to W perp. Okay, yeah. So to prove that y is perpendicular to every vector in W, I need to take the inner product of V with Vi and show it is equal to 0. Yeah, show that it is equal to 0. Okay, so let's put the formula. What is the formula? The formula is V minus x Vi, that is VVI minus x Vi. Okay, I know the formula for x. X was the sum of the projections of V in each of the directions Vi's. So this is the x. Okay, and I take the inner product with every Vi. But Vj and Vi are perpendicular if j is not equal to I. So when I take this inner product, only one term is going to survive from here, and that is corresponding to j equal to I. Okay, so j equal to I, and then this scalar in the inner product, which is in the first component, when I take it out, its conjugate comes out. Okay, so I get Vjv conjugate Vjvi. Okay, j equal to 1 up to k, and when j is not equal to I, this is 0 because Vi and Vj are perpendicular. So I put j equal to I. When I put j equal to I, then I get just Vvi, because Vi inner product with Vi is square of the length of Vi, which is 1. So Vvi and Vvi, that is equal to 0. So inner product of y with Vi for every I is 0. So y is perpendicular to every Vi, but Vi's are forming a basis of W, and therefore y is perpendicular to every vector in W. So y is in W perp. So we have written V as x plus y, where x is in W and y is in W perp. Okay,